multi-hazard performance for RC columns under seismic and fire loading. The multi-hazard performance for reinforced concrete columns under combined seismic and fire loading is a critical topic in a structural and disaster engineering. RC columns are key load bearing elements, and their failure can lead to partial or complete structural collapse. Understanding how these columns behave under sequential or simultaneous earthquake and fire events as essential for improving resilience in built environments. Overview of multi-hazard loading. Seismic plus fire is seismic loading and fire loading. Why multi-hazard? Why multi-hazard design matters? Multi-hazard design matters because real-world structures are often exposed to more than one extreme event during their lifetime: earthquakes, fire, flood, hurricanes, blasts, or human-made hazards. Designing for only a single hazard while ignoring others can result in unexpected failures, especially when when hazards are sequentially or simultaneously. Why multi-hazard design is important? Because in real world hazard interactions, many disasters don't occur in isolation, like post earthquake fires. Example: Kobe 1995 and San Francisco 1906. Hurricanes followed by flooding, blast triggering a fire, or structural instability. A structure weakened by one hazard may not survive as a subsequent one. Next one. The seismic and fire impact on RC. Reinforced concrete is widely used due to its strength and durability. However, when subjected to seismic and fire hazards, especially in sequence, its performance can degrade significantly. Understanding how each hazard and their combined effect impacts RC structures is crucial for effective design and mitigation. Im- Impact of seismic loading on RC structures, like the structural effects are like the cracking of concrete, like flexural flexural shear and diagonal yielding and buckling of reinforcement, spalling spalling of concrete cover, formation of plastic hinges in beams and columns, loss of stiffness and strength. Impact of fire on RC structure is like material degradation, like concrete, steel reinforcement, uh, and the structural consequences is like a loss of cross-sectional area from spalling, reduced bond strength between steel and concrete, risk of progressive or sudden collapse if exposed too long. Compound, Compounding effects of sequential concurrent events. The compounding effect of the sequential and concurrent hazards events, such as earthquakes, concurrent hazards events such as earthquake, so followed by fire or simultaneously seismic and thermal loading, can cause structural systems like reinforced concrete to fail more rapidly and unpredictably than under any single hazard. These combined effects are non-linear, non-adaptive, and pose serious challenges in design, assessment, and emergency planning. What are compounding effects like? Compounding effects refers to how multiple hazards interact to cause greater damage than the sum of their individual impacts. Structures damaged by one hazard are not the same going into the next. Multi hazard events are not just cumulative, they are compounding, and failing to account for this leads to underestimating risk, collapse potential, and life safety threats. Limitations of uncoupled approaches in multi-hazard analysis. Uncoupled approaches treat multiple hazards independently, analyzing each each hazard in isolation and combining results in a simplified way, often ignoring how one hazard affects the structure's vulnerability to another. While these methods are computationally efficient, they introduce serious limitations and inaccuracies, especially for sequential or concurrent events. Example: earthquake followed by fire. What is an uncoupled approach? The perform a seismic analysis, assess damage, then perform a fire analysis on the original undamaged or simplified damaged model. No physical linkage between hazard induced damage states, often used in code based checks or simplified risk assessment. Key limitations are Key limitations are ignores damage progression, no residual capacity tracking, lack of interactions effects, over or underestimation of collapse risk, doesn't capture time dependent effects. The better alternatives like sequential analysis with damage state transfer. Example: transferring cracked geometry and internal stresses from seismic model to fire model. Integrated multi-physics simulations. Example: OpenSeas plus FDS, ABA, QES with user defined temperature histories. Oh, Pro-ballistic fragility modeling with multi-hazard scenarios. Uncoupled approaches can dangerously oversimplify the true vulnerability of RC structures under sequential or concurrent hazards. They fail to capture damage evaluation, residual effects, and interaction mechanisms that are vital for accurate performance assessment in real world or multi hazard scenarios. Simulating real world multi hazard scenarios. Real world multi hazard simulation goes beyond academic modeling by replicating how actual hazards affect realistic buildings or infrastructure using real hazard data, actual building geometry and material specifications, true event sequence, and cascading effects. A real world simulation components like earthquake, fire, other hazards, and structural modeling as built conditions. Use actual RC detailing, geometry from BIM or CAD. Use fiber models or solid elements with proper boundary constraints. Consider non-structural elements, partitions, finishes if fire modeling is included. Modeling is included. The key benefits of a real world simulation is realism, more representative of how actual buildings behave, risk informed, helps generate actionable fragility and resilience curves, design feedback, identify weak points in detailing or materials, economic, a better informed repair or retrofit strategies, emergency planning helps with the first responder and evacuation scenario testing, predicting uh, complex thermomechanical behavior in RC structures under multi-hazard events. Predicting complex thermomechanical behavior involves simulating how reinforced concrete RC structure when exposed to thermal loading, example fire and mechanical actions, example earthquake, gravity and blast, in a coupled or sequential manner. This is essential for understanding how temperature induced damage interacts with structural stresses, especially in post earthquake fire PEF scenarios. Uh, Thermomechanical behavior becomes complex due to nonlinear material properties, coupled coupled phenomena, transient conditions, geometry, and boundary changes. Complex thermomechanical behavior refers to interaction between heat and mechanical stresses in reinforced concrete structures, especially when subjected to multi-hazard events such as earthquake followed by fire. And it's complex because nonlinear and temperature dependent